Good morning, everyone. Welcome to the second lecture on big data today. As usual, there will be a quick revision of the previous session, so we're all on the same page. We started last week and saw that the amount of data is growing extremely rapidly. Most of today's data is stored digitally, so we need tools and systems and methods to store and process that data. We looked at various definitions, like what does big data mean, the three V's, where the term big data most likely comes from. We saw some plots from market reports, how the amount of data keeps growing. We have also then looked into a typical setting you would be dealing with if you work on machine learning projects here, but the real world settings are different because the amount of data you have just doesn't fit on your computer, and you need far more computing power to process the data. And then we talked about the organization of the course. I will open the portal in which you can pick the design pattern sometime in maybe 2 or 3 weeks. So we don't need to do this yet, but I'll inform you in iLearn once I make this available to everyone. And we've talked about some books and various, we compared a few companies and we saw what they have in common, which is not just that they have a low number of physical assets, but they're also data-driven. We saw how the worldwide economy is changing. And some other examples. And I talked a little bit about CERN and big data problems there, as well as some work I have done previously on detecting electricity theft. Then we said we want to deal with big data, so we need to take advantage of parallelism and not just a single core. And that's why we started with a few terms. We looked into processes and threats, and we looked into concurrency and parallelism. We discussed how you would define it and how I would define it. And I think overall we converged quite well, especially the terms concurrency and parallelism are sometimes confused. And I think this one Stack Overflow article addresses this quite well and how to define these terms. Anyone looked into the Stack Overflow article? If not, have a look at it. I think it's overall a good explanation. A friend of mine, he's actually an expert in this kind of stuff, and he told me he applied for a professorship maybe 10 or 15 years ago at various German universities. And when you apply for a professorship, you need to give two talks. One is more like a short lecture, and the other one is a talk about your specialism that you can pick. And his mandatory lecture part was about concurrency, parallelism, and he defined it, how he sees this. But then you have other professors from that university sitting in that lecture, and they are assessing you and asking questions, and they totally disagreed with him. And they said to them, all of them in that department, concurrency and parallelism, it means exactly the same. So they totally disagreed with the way he saw it, which is, sort of strange. But I think he finally got an offer at a place that suits him more than that place. It has nothing to do with this university, obviously. It was in a different state. So you see, defining this properly is tricky. I think we've looked at good definitions that also make sense. We've seen how you as an end user are dealing with multi-threading, and we will now start with a small coding example. And I will also share my terminal, and I want to try something with you, and we'll see a small example of or for what parallelism could be useful. Imagine we have various URLs, various pages, and we want to crawl them. And probably you know how you can access a URL through Python, for example, with URL lib. And you could do something like URL lib dot request dot URL open, and With that, you can open a URL. But we don't want to do it that way because we have all these pages, and if we download them sequentially, how long would you maybe guess would this take if we have these, I don't know, 10 or something like this pages? If we download them sequentially, any guess? Just web pages without a lot of content, so just text. Yeah. Something maybe like 10 seconds, yes. Not because these pages are very big, but because of all the latency in the network, which also slows us down. But if we just used this as a single thread, we try to download the first page, but then for a long time, our CPU is actually just waiting for the network because we have all this latency in the network. And then once it's downloaded, we process it very quickly to store it in our list, and then we start with the next page. So most of the time, our computer is actually just waiting for the network in these, say, 10 seconds or 5 seconds, whatever. So we want to take advantage of parallelism, and we want to be able to download multiple pages at a time. So we have multiple threads, for example, and they would just be taking advantage of parallelism. And then we have, say, 4 cores or 8 cores, and we take advantage of them and overall speed up the downloading. We will not reduce this to 0, obviously, because there's still latency, but we can try to speed that up. And we can do this in a very simple way with a thread pool. Later, we will also see the difference of threads and processes in Python and what impacts can be there. But we're now creating a helper function. And this helper function is called open URLs. And I have a parameter, the number of threads. And then I have a thread pool. And the thread pool I initialize for a certain number of threads. Has any one of you ever used such a thread pool in Python? Okay. What have you used it for? Mm-hmm. Okay, so you have probably done something quite similar to what we're doing now. So a thread pool means we initialize it for a certain number of threads and then say 4. And then we try to have 4 threads working. And then one thread has finished with its task, it will continue with the next task. And it's up to us for how many threads we initialize the thread pool. The beauty of this thread pool is you don't need to worry about synchronization or locks or all these issues that can arise when you deal with parallelism. You have seen some of these mechanisms in your operating systems course. But with this thread pool, it's actually quite simple. We just create it, and then it has a map function. And the map function means we want to apply a function to multiple entries. And the function we want to apply is called URL request URL open. And this opens the URL. And we want to apply this to this list of URLs. So not just to a single URL, but to multiple. And then we create a thread pool. And we run it. And eventually we close it and join it. And now we can try this, how long it takes, for example, just for a single thread. So we don't take advantage of the thread pool. We just say we take a thread pool with 1 thread. So eventually it's still sequentially. So it took around 6 seconds. So the guess of 10 seconds, whatever, was fairly okay. And now we can try to do this with 2 threads, which should already lead to a noticeable improvement. So speed up about half. There's always network latency, so it's a little bit difficult to reproduce this, and there may be a cache, whatever, on top. But we see there's quite a speed up because now we have 2 threads in this pool, and the first thread starts to download the first URL, then the second thread, the next URL, and once the first thread has finished, directly the thread will use again the next entry from the URLs list, and so forth. Now we can try this for 4. We see there is still a speed up. Obviously, we cannot speed this up to near 0 because there is latency. And imagine our URLs list is huge. say we have 1,000 entries. Would you think it would be great? We create a huge thread pool with like 500 threads. Is this something you would be doing or not? Yes. So maybe something in the order of the number of cores that your CPU has, or maybe a little bit more, that they try to share some time, but don't create too many, because if you create too many threads, this whole system will just be busy with administering this and giving you time slices on the CPU. But already if we have 4 or whatever, it speeds up. We can try for 8. Some point the return will also diminish, but there is a speed up. And now imagine your USLs list is much bigger than just 10 or 12 entries, whatever, but a few hundred entries. You will be able to massively speed this up with the thread pool. And the thread pool is nice to have. You don't need to worry about locks and syncing. It's all just done for you under the hood. And you said you have used this for something quite similar with a REST API or something. Yeah. So this will give you a good speed up and is easy to use. So take advantage of these tools. You have them at hand and they're fairly easy to use. If you, well, probably just shared the wrong thing. Need to try again. What you see here in the slides is just what we have done. Imagine the URLs list is much longer, and this is how to use the thread pool. And when I ran this a longer time ago, you see it took a little bit longer, but depends on the network overall. And but we see there's also a speed up, and we were able to reproduce a comparable effect here. So this is a thread pool. And if you're curious about how to create threads or how to do multi-processing in Python, there are some good resources on the internet. Feel free to look at them. I have taken a little bit of content from there. So they are also credited here. And but I've also come up with some of my additional explanations and a couple of things I want to show you. And today we'll do quite a bit of live coding. So we see also how to use all of this. And we will try the next example. Just for the ones in the room, you obviously get to see already this because I only have a single screen. For the ones online, you just see the screen share. I want to try out something now. I want to measure how long it takes to do a computation. And if you have taken my algorithms and data structures course, which most of you have seen how we can measure how long a computation runs, because there's a reference date in our environment. It's typically the 1st of January, 1970. And you click or you open the time function and it gives you the number of seconds or milliseconds, whatever, since that reference date. You measure, then you run your computation, you measure again, and then you have the difference between the end time and the beginning time, and that's how long your computation took. In an algorithms and data structures course, you care a lot about complexity, and there are good reasons for thinking about complexity, but sometimes you also need to measure running time because this is eventually what your customer expects. But for most algorithms, if they have a good complexity, their running time is also far better than for an algorithm that has a bad complexity. There are obviously exceptions, and we will try this now. We will import the time module. We will also need to work with threads later, so we can import this already. Has any one of you ever created threads manually in Python? Because you used a thread pool. Has anyone ever done this? Maybe if you have, just raise your hand, but doesn't seem so. And I'll show you now how to do this. So one person has raised his hand. Maybe you want to tell us briefly, either in the chat or turn on your microphone, what you have created threads for in Python and how. We're more than happy to learn what you have done.
Yeah, so if I remember correctly, I was trying to implement from scratch a API that basically takes an image and classifies that image, and I was trying to offload the whole network into a separate thread, which in hindsight was a little bit dumb at the time.
Okay. Yeah, thanks for sharing this. We will now see how we can actually count down a very large number. So we have a very large number that we want to count down, say 50 million. And it's obviously a toy example, but it will soon show us in the next step how we create threads in Python. And then something strange will happen when we try to speed this up. So the countdown function, we pass a parameter n, and we count down until n is 0. And we now actually want to start measuring the time. So we say, this is the current time. I'm now entering multiple statements, so they get executed sequentially, because if I first measure the time and then type in this interactive environment, the next command, most of that time will actually spend while I have typed. So in this interactive environment, you can do this with Control O. You can type in multiple statements that get executed. And then we want to call the countdown function for this large number, 50 million. And then we measure the end time. And this should run very quickly. And we can see that this takes about 2.6 seconds. Now we could think we can try to speed this up by doing something slightly different. We could create two threads in Python, and we could have one thread count down from half of this number to 0, and the other thread as well. And since I have multiple cores in this computer, I would assume I can speed it up, right? And we can try this out now. We can create a thread in Python, and we're calling the constructor, and the target is a reference to the function we want to be running. And we also have to pass a list of parameters, which looks a little bit ugly, but the syntax here means it's a tuple of arguments. And if I just put parentheses around it, it's not a tuple. So I need to put in this comma just to indicate it's a tuple. If you have dealt with such details in Python, you must have seen this. So for half the count, which means 25 million, and we create a second thread to do the same. And now we're running this experiment again. We say, the start time. We want to start the first thread, then start the second thread, and then also to join the thread when it's finishing. And then we measure the time again. And then we see, well, this hasn't really led to any speed up, which is strange because I think I have two threads and I put in half this number, and I think I would speed it up. Maybe not precisely to 1.3 seconds, but at least something far better than my 2.6 seconds. And we will now look at what's the issue that's causing this. If you're trying to run something like this in Java or C++, you will probably not notice an issue, but in Python you are. Last week, I mentioned the global interpreter lock, and I think there were one or two students here who knew about this. Maybe, is that person here from last week who remember the global interpreter lock? Okay, so I mentioned it yesterday very briefly when we started the discussion, and now we'll come to a limitation in the Python environment, which is called the global interpreter lock. There's a lot of text, but this is just for your revision what it's about. When you run multi-threading, you can obviously experience lots of problems, because when we talked about last week the differences between threads and processes, we saw that in a thread, we share memory or in a process, we share the memory among the threads. So we can run into all sorts of strange problems when we have threads sharing memory. And that's why in an operating system course, you learn, for example, about locks, that there are locks in which only one thread can go in at a time. Locks may help you to solve these issues, but they can lead to new issues because you may run into deadlocks or this kind of stuff. And that's why overall multi-threading is messy. Multi-processing is different because in multi-processing, these processes, they don't share data directly, so you have less of such issues, but they need to communicate, and when you communicate among processes, this can lead to new problems. So somehow we must build something. If you look into C++ or Java, you can work with locks. One way how to avoid issues when it comes to working on shared data. But in Python, it works a little bit differently. Because in Python, there is at least in CPython, so the default or the most common implementation in Python, there is a single lock on the whole interpreter. And that means there's no fine level locking, but there's just one big lock on the interpreter. And that means you can only run one thread at a time. And this helps us, at least from the Python philosophy, to not worry about shared data among threads, because only one thread at a time can run. So it prevents deadlocks, because deadlocks can be a consequence of locks. And if we only have one lock, deadlocks are not an issue, and leaked memory is also not an issue. So creates a lot of safety, but eliminates speedups, because I cannot effectively use multi-threading in Python. Now you're wondering, why does something like this exist? Because it sounds quite stupid, right? To have a global interpreter lock, because this is not the idea of locks. In like Java or C++, you have more low-level locks. And there were some good reasons in the past why the global interpreter lock was introduced. A lot of people claim that global interpreter lock was a very bad choice. However, others, like Larry Hastings, they claim it was actually a good choice, because that was one of the reasons why Python became popular quickly. Because Python is Python is very popular nowadays, but Python goes back, I think, the early 90s or something, when many operating systems did not have the concept of threads yet. So multi-threading and locks were not really an issue, but Python was designed to be easy to use. And what they wanted to do in the early days was to just use a lot of C libraries in the backend, because also that's something we still do nowadays. For example, in scikit-learn and other libraries, most of the code is not implemented in Python, but it's implemented natively in C, C++. So it runs faster. And a lot of these existing C libraries had to be integrated in the Python environment early on, so there were a lot of features actually available. But these libraries were also not thread safe. And then the GIL, the global interpreter lock, helped to just make all of this stuff thread safe that wasn't thread safe by avoiding multi-threading. So there's a lot of criticism, but it was very easy to implement. And you could easily integrate all of these C libraries that were already existing at that time. And Python was also readily adopted because all these features were available. And then with the global interpreter lock, one didn't run into blocking issues. There's some more resources that you're welcome to read. We will later see what's actually the future of the global interpreter lock. But now we still want to, take advantage of parallelism in Python. So what we have just tried to implement in this interactive environment didn't really work out. But we can try to run this again. And, well, I've now coded a lot. I'll just show you this actually in the slides. And then I don't need to code it again because it's more or less just the same what we have done, but we're actually using a multi-processing pool. And this actually uses multiple processes, not multiple threads. And you can also try coding this at home to just see that it really works now that I'm not coding it. And we are now creating two processes that should do exactly what our two threads from before should be doing. The syntax is and the signature of these methods is slightly different, but I still pass a reference to the function and then here a list, not a tuple of parameters for half the count to each of the two processes. And I run it and I see it leads to about double or half the runtimes or major speed up. Because what I'm doing now is I'm not creating threads, I'm creating processes. And if I have two processes, I'm not affected by the global interpreter lock. And I get my speed up. But once I have processes, I have the issue that processes also need to communicate. And inter-process communication adds some challenges, but can be done. But I don't have that issue of shared or leaked data because processes are separated in the operating system in terms of their RAM. And with two threads, you can access the same memory in a process. This comes obviously with some new consequences because starting a new process is also computationally more expensive than creating a new thread. But like this, we can actually speed up, and we can actually speed up quite a lot. Now there's the big question, will this global interpreter lock be removed? Because it seems like, yeah, it's from the 90s. We wanted to use all these C libraries, and somehow it's a big limitation of Python. I heard people already arguing about this in 2011 when I started with Python, so 13 years ago. And there are a lot of complaints. But if you remove the global interpreter lock, you need to add some safety mechanisms because otherwise you will run maybe into all these issues that the global interpreter lock try to avoid. And there are various discussions about this. And if you maybe heard about Guido van Rossum, anyone heard about Guido van Rossum? Yeah, he is the sort of creator of Python. And he was asked whether the global interpreter lock could be removed a couple of years ago. And he said, well, in Python 3, it could be done. But we also would need to make sure that if you make these changes to the Python interpreter, that single-threaded programs don't run slower than before. Because if you add a lot of complexity in the interpreter, and a lot of computational tasks are still just single-threaded, we don't want them to run slower just because the interpreter gets more complex. Guido van Rossum is known or is called the BDFL. BDFL is a term often used in open source projects because he created Python and was leading the project for many, many years. And a BDFL is the benevolent dictator for life. This is sort of a term used in the open source field to describe that guru who is in charge of an open source project. Meanwhile, I think he has changed his career a little bit. I saw Guido once when I studied in London at Imperial College. He once gave a guest lecture. And so this was, I think, in 2015, there, a lot of the people in the audience also asked him about the global interpreter lock. And he said he didn't find a solution. And if someone who is smarter than him came up with a good solution how to eliminate the global interpreter lock, he would be most happy. So that was the discussion in 2015 when I saw him when he gave a talk. And recently something has happened, and we will look at that very quickly. But there's not just CPython, because I mentioned this is all an issue in CPython. I guess most of you have installed CPython. This is just a standard Python implementation. but which is in the background implemented in C, C++. There are obviously other Python implementations like Chython, which is based on Java. There is PyPy, so Python based on Python. The various other implementations. And PyPy, so Python based on Python, has a global interpreter lock, and Chython and other implementations, they have no global interpreter lock. But I think those are niche implementations. Most of us probably use CPython. Is anyone in here who doesn't use CPython, who on purpose installed one of the other implementations? Probably not. I also haven't tried them much, I have to admit. But there are other implementations like Cython. So this is not a typo. Cython is not a typo of CPython. Cython is you can compile your Python code to C, C++ code, and then run it more efficiently. But you need to bear a few things in mind, like typing and so forth. And for Cython, the global interpreter exists, but it can actually be temporarily turned off. And this is what this lecture also looked like last year. And then so I have my news feed here in the phone, and just 1 or 2 weeks ago, something popped up. There's an update about the global interpreter lock. I thought, I already uploaded my slides, but then I've updated them because something has happened. Recently, a new release of CPython was made available, 3.13, in fact. And this one comes with a build time flag, disable the global interpreter lock. And there are actually now 2 application binary interfaces available, so 2 ABIs for CPython, one with the global interpreter lock on and one without. So now there are both ways you can go with the standard CPython. And the goal is that sooner or later, the CPythons, or in the coming years, the global interpreter lock could be controlled with a runtime environment flag. So when you start the interpreter, you could pass this as a parameter. So we're not there yet, because you can either build the interpreter with or without the global interpreter lock. So you have these 2 binary interfaces. In the future, maybe there's one binary interface. When you call the interpreter, you can put an environment variable whether to turn on the global interpreter lock or not. This is supposed to be probably happening after 2 or 3 releases, so probably 2 or 3 years from now. And then the hope is that towards the end of the decade, maybe CPython would turn off the global interpreter lock by default, and we would still be able to turn it on if we wanted. By default, it would be off. So this could be the roadmap for the next 6 years, 4 to 6 years, something like this. But one will need to see how the Python community evolves, because we obviously have all this legacy code and old libraries. They need to be amended in order to be working. But a lot has happened since the early 90s, when there was a decision to introduce the global interpreter lock, because we were reaching then at the end of the decade, the year 2030. So it's a long time. And I'm just very excited to see how this is going, because it could lead to massive speedups in Python, because we can use then multi-threading very well, like in other languages, but there's still some work to work on all the legacy code. But just a few years ago, everyone started switching from Python 2 to Python 3. I don't know, did anyone ever use a view Python 2 in the past? So I'm too old. Yeah, you as well. So I used Python 2 10 years ago, and we also have some hands raised. And at some point, I also switched then to Python 3 when it became more popular. And some code had to be amended to be working. I think the transition wasn't that much. I think it largely affected the print statement, which was not a statement anymore, but a function, plus some other things like range, which was a list. Now it's a generator, plus a few other things, but some code had to be amended. But then with this future Python 3. I don't know, 3.20 or whatever, maybe there's a bigger migration of code necessary, but it's slowly happening over time. And it actually also happened like this slowly over time from 2 to 3, because if you were in Python 2, I think you could import some stuff from Python 3 and then slowly update your code and make it working. So there's something like this happening here as well, and we'll see how it's going in the coming years. But because of big data and working with ever larger data sets, we need more parallelism. We have more cores. So this is probably a good choice. And a lot has simply happened since the early 90s. And this is a slide I just created 1 or 2 weeks ago, just before the course started, because it popped up actually in my newsfeed on the phone. Now, we could obviously discuss parallelization the whole term and only talk about parallelization and look into all sorts of details of locks and so forth. But probably there's a question about how much parallelism do you need in practice? And most of you here are studying AI. And maybe I ask you first, what do you think when you work as a data scientist, data engineer, how much do you need to know about parallelism? You need to be an expert, or some basic knowledge maybe enough? Any guesses? Also online, if anyone wants to turn on their mic. We have in the chat, one student says mid-knowledge. I think this approximates this quite well. Probably you don't need to be a huge expert unless you do some very specialized tasks. But there's actually a lot of parallelism under the hood in your libraries nowadays.
That's exactly what I want to say. I think overall for machine learning, parallelism is really essential. But nowadays we have just such frameworks as TensorFlow, Keras, or whatever, which already handle a lot of this parallelism stuff underneath the hood, so that we as the user of a more overview perspective don't need to deal with it personally, but the libraries deal with it internally.
Yeah, I think that's a good statement. It's obviously essential, but it will be under the hood in a lot of libraries. So you as a data scientist, it's important to know, but you don't need to be an expert in how to write highly parallel code for most settings. And maybe some of you do, but then you can also catch up. But maybe let's think about what others say. And there's obviously some interesting thoughts I found, like Donald Knuth. He's the inventor of TeX, which is the basis of LaTeX. And he also wrote these 4 or 5 big computer science books. I don't know if you have them at home, but I forgot the name now of this book series, but he tries to cover all computer science in his books, and I think 4 or 5 or something are available, and he's been talking for 20 years to make the next one, but somehow he's not finishing. I actually bought them a few years ago and have all these books from that series at home. Once I bought a house and I knew I wouldn't have to move anymore, and I updated my library. So he's a very famous person, in fact, and he was asked, how important is parallelism? So there was an interview a few years back, and he said something like that over the past 50 years, he had written thousands of programs. Many have a substantial size, but he cannot think of even 5 of those programs that would have substantially improved by using parallelism or multi-threading. He has written thousands of programs, but not many would have actually benefited. And then he refers to TeX as the basis of LaTeX and says that that would be no help because that's a highly sequential thing to build a TeX document. But then he says he knows that there are some important applications for parallelism, like rendering graphics. So nowadays, training neural networks on graphics processors, breaking code, scanning images, simulating physical and biological processes, etc. but all these applications require dedicated code and special purpose techniques, which will need to be changed every few years. So he says, first of all, he cannot think himself about many applications, but he knows there are some important applications that others are working on, but it's very dedicated code, very specialized techniques, and they change every few years. What do you think about his statement? Do you agree with this, or you don't agree? Yeah, I also agree to some extent. Probably most programs I wrote as well, they wouldn't have really benefited from parallelism. However, nowadays there are more applications that require parallelism. We all are here in the AI world, and I think what has also changed since that interview is not just that there are more AI applications, but also we have more cores on our devices. Because in that time, the interviews quite a few years back, probably smartphones were quite limited, and also CPUs. Now we have more cores, so we can also take more advantage of that. But yes, parallelism will be not a solution to every single problem. A lot of computational problems are probably inherently sequential. We will later or next time, whenever, see how Google started approaching this a long time ago, because writing parallel code, at least if you want to do it right, is tricky. And Google also noticed that as a major limitation in the early days, and they came up with something called MapReduce, which we'll also look at, and it's still a foundation or an inspiration to many more approaches nowadays that are more advanced, but we'll see that. I think what you will notice is, and we've already talked a little bit about this, when you try to write your own multi-threaded code, at least with all these low-level features, it's tough because you need to think about locks, synchronization, shared resources. But a lot of APIs that you use in the AI world, they offer this under the hood, and you can use multi-threading or parallelism in general from a relatively abstract perspective. For example, in scikit-learn, say we have a random forest that we want to train. So we have many trees we want to train. This is actually something I can parallelize extremely well, because I just need to split the data set once. And then I keep training all these trees. So I could train all the trees in parallel, and then I'm done. And this is just a very simple data set, but think about a bigger data set. And I create a random forest classifier, and with an extreme example that I want to have 100 trees in my random forest. Are you all familiar with how a random forest works? Maybe raise your hand if you know about a random forest. So some are not. So a random forest works like you all know how to train a decision tree because you took my algorithms and data structures course. And now decision trees, they tend to inherently overfit, because they try to learn every single detail if you do it wrong, and then they will learn too many details in your training set, and they will heavily overfit because it just becomes extremely large. Now, you can think about how to eliminate that problem. One thing you could do is pruning, for example, that you don't want the subtrees to get too long. But a random forest is a different approach, and a random forest works with that you take your initial data set and you split it into various subsets. For one easy way could be you have like 100 subtrees, and you split your data set randomly into 100 subsets based on the rows. You could also split it in a different way in terms of the columns, or combine both approaches. So you will somehow randomly split your training set into a certain number of subsets. That's why random forest. And then you try to train a decision tree on each of these subsets. And the goal is to build small decision trees, because you can also control the training of a decision tree learning, for example, by limiting the number of levels you want to learn, and a couple of other things you can set. And then you have trained your random forest, and when you make a prediction, you put in the example in all of these trees, and then you, for a classification, for example, you make a majority vote. For a regression, you could take the median or other things depending on your use case. So this is the idea of a random forest. And now if I want to train a random forest, I have a certain number of subtrees. For example, here I can say I want 100 subtrees. And now if I train this sequentially, it will, not on this data set, but on a large data set, it will take quite some time. So I need to train many, many trees. But you can put the parameter n chops. I don't know if anyone has seen this. If you have seen this before, maybe raise your hand, the n chops. And n chops, you put in a certain number of threads or processes, whatever you want to be using. Like 4 or 8, depending on your machine. And then you can speed up and you can train 4 or 8, whatever trees at a time. If you want this to be flexible and just use the number of cores you have on your machine, because some of you may have 8, others 16 cores, you just put in -1 and it takes the number of cores you have available. And so you don't need to change the code if you run it on a different machine. So this is something you will find not in all models in scikit-learn, but in various. And if you, I don't know, use Keras or other libraries for neural networks, you can just change a flag and say you're working with a GPU, and the code is then compiled into CUDA or whatever. You use a different vendor. That's obviously not just NVIDIA. And then you can compile this automatically and run it on the hardware. You get massive speedups. Maybe the speedup is not as massive as if a real pro wrote the CUDA code for you, but if you don't know how to write CUDA code, it's a massive speedup that you get extremely easily. So this is offered to you under the hood, and I think you mentioned something like this before when we discussed it. So take advantage of this stuff. A few years ago, I had access to a big server. I don't know when that was, 6 or 7 years ago. So time is also flying. That one had more than 100 cores in the CPU. It was new in the lab in which I worked at that time, and I was the first one accessing it, so I didn't need a virtual machine. I could directly use it and take all the resources. And then I had to train a huge random forest and many of them because there was a huge cross-validation going on. And I had a huge data set, and I could actually then use all these cores, I think 140 cores. And my experiment ran for 1 week, training all these massive random forests. But I got finally a very good classifier that I could pick. There was also cross-validation. There was a hyperparameter optimization, trying to find the right hyperparameter settings for the tree, like the number of levels and other things you can configure. So that was pretty cool, and it's something I wouldn't have been able to run on this laptop to that extent. So I used this big server, and I was the first one in the lab trying to use it. And before the others learned about this server, after 1 or 2 weeks, I could just run all my experiments and had better results for my next paper. And then everyone in the lab wanted to use this machine. And yeah, you got a smaller virtual machine on it with maybe 20 cores, not 140 cores anymore. So and this one is something you can use extremely easily. There are obviously internally this in scikit-learn, it uses choplib, which is a Python library used for parallelism. It uses multiple processes, not multiple threads, but some classes in sklearn, in Cython, they were already in the past somehow able to internally release the global interpreter lock with some hacks. It's probably something that will also start to disappear in the coming years when you can anyway disable the global interpreter lock. There are other approaches to parallelism, like, for example, asynchronous programming. It's something that has existed for a long time, but starting to become more popular. In asynchronous programming, use in Python the async and the await statements in order to use asynchronous programming. Asynchronous programming is a form of parallel programming and it allows units to run separately from the primary thread. Compared to multi-threading, multi-processing, this is less memory heavy and also accredited with enhanced responsiveness and performance. Learning how to write asynchronous code is a little bit more tricky. There are some references in here from realpython.com in case you want to study this. We're not discussing it here in the course, but it's something I notice has been more popular in the last few years. A little bit more tricky to learn, but also not that difficult. Maybe give a look at it. But I think with what we've done so far, it's already plenty of new things you're exposed at, and the asynchronous programming is maybe something you would learn at a later step. Now we have studied the introduction to parallelism, and parallelism is a foundation to processing large amounts of data, which we will now look at in this big data architectures chapter. And concretely, we will look into distributed systems. We will look into MapReduce, an early approach by Google on how to write parallel code without being an expert in multiprocessing. Because Google has very smart people, but they also noticed in the early days, even if they have very smart computer scientists, most of them are maybe not that great in writing highly parallel code. So they came up with a shortcut of allowing everyone at Google writing parallel code by rethinking how to solve these problems. Then there's the CAP theorem, which is a fundamental limitation of distributed systems. And we will look into this, and then we'll see a little bit of how we can actually speed up computations through GPUs and FPGAs. And especially that GPUs are extremely popular nowadays for training neural networks. Before we do that, we will do a quick revision of database management systems. Concretely, relational database management systems. It's something that all of you, at least the ones studying the AI bachelors, have learned. I think in your third semester or something, you have this relational database or the database class. Who of you still feels comfortable with that stuff you learned there? Okay. It's a key skill that you should practice. And because when you work in industry, typically you will not just have a CSV or Excel file in which you have your data set, but you actually need to load it from a bigger database. And that's why make sure you're comfortable with that. And we will do, so when I taught this course in the past, when I taught it for the first time, and I think I said this last week, those were students from a fast track bachelor's who had studied some technical subject before, and they had not seen databases that often. That's why I had a bigger revision of databases in there. But now this course is only taught to everyone in their regular AI bachelors. So I'm expecting you to know that. Nonetheless, there are maybe like 5 slides just to make sure we're on the same page. I will not have like a lot of queries in there, but we more think about some guarantees and some properties of database management systems, because we will contrast them to other guarantees or assumptions made in big data environments. So when you work with a relational database, you work with tables. What you see is when you create your tables and how they relate to each other, you think about the conceptual schema. So you have these tables and I have these columns and certain keys, whatever, and I can link them with foreign keys and so forth. This is your conceptual schema. Then when you query, you can create filters. So you select a subset in this database, or you aggregate the data in some way. You've learned this in detail, how to write SQL queries. And internally, the database somehow needs to store your data efficiently. And what's often used is some variation of B trees that are something that works quite well for storing large data sets from a relational database. But you as a coder, you don't really deal with the internal schema, you deal with the conceptual schema, which is the your structure, and then you write your queries. But internally, you don't care too much about the B trees. Then you not just have your database that stores this data, but you also have a database management system. Because in a database management system, you do more than just storing your data, but in fact, you want to handle transactions. Anyone can still define what a transaction is in the context of databases or database management systems? Yeah. Mm-hmm. Okay. Yeah, a transaction means I may have multiple steps within the transaction, but the transaction can either be fully executed or it's fully unrolled in case something goes wrong in between, because I don't want to have an inconsistent database. For example, I have one query that prepares something and then a query that updates something and then updates something in the next query. And if there's some error in between, I would leave the database in an inconsistent state. And that's why the transaction manager would unroll these partial changes then, and I can either have a transaction fully executed or not. So there's nothing in between. And this is a key property of relational databases, makes our life much easier, and we can all sleep better because our banks use this and our bank accounts would hardly run into an inconsistent state. And that's why you need more than the transaction manager. You would also have a scheduler because you may have multiple transactions running at the same time. So you also need to think about parallelism because there could be two transactions that are completely independent, just two queries that just query stuff, they don't change. You can just easily run them in parallel because they don't affect the database. And you don't want to run this sequentially. You want to run it in parallel just to speed up computations. But there can be also queries that change the database. And for example, if you have one query that changes one table and a query that changes a totally different table and they're not related through foreign keys or whatever, then it's probably fairly easy to update them in parallel as well. But then maybe you have other constructs. For example, you have one query that changes a table, and you have a query that reads from that table. And maybe that making those changes takes very long, but you don't want to read out only from half the table that got amended. So if you run the changes first, you would complete them and then run the query that reads from there, because you want to avoid inconsistent states. So a scheduler needs to take care of this. Obviously, you want to have as much parallelism and speed up as possible, but there must also be locks to avoid inconsistent results. And there can be all sorts of other strange occurrences that you have two queries that amend, I don't know, the same table or something. And you cannot, sometimes you can run it in parallel, sometimes not, depending on how much they would affect each other. And you, as a coder, you don't want to worry about this, and that's why your scheduler handles all of this, combined with the transaction manager in case one of these transactions goes wrong in between. And then you need other things to recover the previous state. You need some buffer to speed up, and you want to write locks. You also want to have, obviously, a disk where you ultimately have stored the results persistently, and so forth. So this would be typical features you have in a database management system. So that's something important because this comes with various guarantees that we're looking at in a moment. Indexes are also important. Anyone, maybe without looking at my slides, who remembers what an index is on a table? Yeah.
Like a pre-selection or a subset of the data to access a specific requested data, or let's say that's requested more often faster. For example, if I knew for example, for the THE, there will be, for example, an index only for professors to easier access the data from the professor out of all student professors.
Yeah, an index would allow us to speed up queries, would bring us, for example, some structure in the data, or the data could be sorted in the index, whatever, so we can access the data quicker. This is the advantage of an index. However, when you amend the data, the index also needs to be amended. So it makes no sense to create an index for everything, especially if you maybe have much more writes than reads. But depending on your setting, if you maybe have much more reads than writes, an index can help on certain columns, or you can even have a joint index on multiple columns, and this can speed up query performance. But when you amend your data, the index will also need to be updated, which takes time. Some things are typically indexed by default, like a key, for example. When you say this column is my key, that's typically directly indexed. You can also see this in your database management system often, what's an index, what's a key, but oftentimes keys are directly indexed because you need keys all the time, also for foreign keys and so forth. Integers are very easy to index. Strings are more difficult to index. So a full text index is something that is more complex to build. So that's a little bit an overview about an index. And then another important term is database normalization. Anyone remembers this term, normalization? Maybe raise your hand if anyone remembers this. Okay, do you also know what it is? Okay, we can, for example, look at this table here. It's a very stupid table. You wouldn't build it that way, but we're looking at it. So it somehow stores skills of an employee. And we store many things in this table. An employee has an ID. We want to store skills, like an employee is good in public speaking and carpentry, but somehow we also store more data of this employee in there, like his or her address. And now we have the same address multiple times for this employee. This leads to various consequences. It can lead to the consequence that we need more storage if we do something like this many times. But also if we change the address of this employee, it can happen, maybe we don't affect all the rows and we create inconsistencies because we have this redundancy of data. And we don't, and this is what actually has happened here for employee 519. Somehow we have multiple addresses for this employee. Maybe just the first row was amended and not the second one, or vice versa. And this creates lots of issues in our data integrity. And that's why we care about database normalization. In normalization, we want to avoid such redundancy. And for example, we would create a new table with an address. And then we have the table address, and we store the address once per employee. And from this table, employee skills, if we really want to store his or her address in there, we just put in a foreign key to that other table where we store the address per employee exactly once. There are all sorts of different so-called normal forms. I don't know when you took your database course, because some of you remembered normalization, if this is something you discussed, these different normal forms or not. Yeah, there are many different normal forms. And if you, then you become increasingly more normalized, but just normalizing more and more maybe reduces redundancy and increases integrity, but it will make your query performance also worse because you need to add more joins in your queries. There's again some compromise. This table here is the advantage. If you want to query all of this, maybe you don't need joins because joins are expensive. And if you branch out your data throughout many different tables, according to these normal forms, if you go to a very high normal form, very expensive one, maybe you have very little redundancy in it, but just querying simple stuff could be very complex because you need to do all these joins. So it's again a compromise you need to make. But this one here is certainly not a great table, and it needs to be normalized at least a little bit, that we get rid of something like this. And also I would normalize the skills, because skills or some employees can have the same skills, and maybe you then have typos in it, and you type in public speaking or carpentry, and you have some typos when this data is entered. So you don't want to store that as like this, but rather you have a skills table where you refer to with a foreign key from the employee skills. So you would store which skills that employee has, but the skills are stored in a different table, just to avoid typos and all of this. So that's important. And then relational databases, they come with very, very strong guarantees. And the set of guarantees is something we call ACID. Relational databases, they have been around for, I don't know, 40 years or maybe longer. And there is some criticism towards them. Some people say, well, they are not fit for the big data age, but in fact, you can scale them also to a lot of data if you do it right. For some use cases, and we will see them in the second part of this chapter, for some use cases, maybe relational databases are not the right thing. But I think for most use cases we still have today, relational databases are extremely helpful. And I think we still use them so much because they come with these guarantees. And ACID stands for a set of properties that relational databases guarantee in the context of transactions, and all sorts of things can go wrong, errors, power failures, whatever. The A stands for atomicity. And atomicity means that a transaction is treated as a single unit, and the transaction is either fully completed or completely failed and then unrolled. So you cannot have a transaction run partially. So this gives us already something that is very helpful, because a transaction works or it doesn't work. However, I've noticed a long time ago, for example, I used MySQL, one of the popular relational databases, that it had various engines in the background. One is an older one that was, I think, called MyESAM or something like this. And that one was used in a project where I once worked on. And I wrote a lot of code, you know, with transactions, and I tried to run it as a test, and none of it worked because this was an old engine that you could pick in MySQL. And that one didn't allow transactions, in fact. And then I had to rethink all my code, but the BDFL, so this Benelovin dictator for life in this project, he wanted to keep it that way because he said there are certain properties in this MyESAM we needed. I disagreed with it because performance was definitely not an issue of the other engine that would have offered this. And one of the senior engineers in the team, he said, these transactions are not that important. He said, we're not a bank, we're just a document management system. And then I had to write a lot of code around it, trying to build atomicity, but obviously it was not fully guaranteed. So that was sort of painful. So, but this was more than 10 years ago. I hope no one uses this MyESAM, or what it was called, engine anymore. So always make sure for new projects, you actually use something that offers these guarantees. Then we also have a D in ACID, the last character D. D stands for durability. So this guarantees once your transaction is completed, it's durable. So even if there's a power failure, whatever, or a system failure, it's written on the hard disk, or at least somewhere stored, that it's durable, that it can be restored, even if there's directly a power failure. So transaction completed means durable. Then the I means isolation, that you isolate these various transactions from each other. I've mentioned some examples before. There are some transactions that you can easily run in parallel, just like two queries, for example, that just read and there are no changes. That's fairly easy. But once you have all these changes going on, or changes and reads in parallel, it gets more complex. But that this is treated correctly, that you have eventually a consistent result. That's meant by isolation, and consistency means you have a consistent database and you run a transaction and you will still have a consistent one. And if you look at relational databases, you can also define, I don't know, the type of a column and this kind of stuff. And this is all made sure that it stays consistent and you cannot just put in some wrong data in a column of a different type. So atomicity, consistency, isolation, and durability. This, I guess, is something you also saw in your introduction to databases. And now you're wondering, why am I revising this? Because we'll now go into the big data world where we can use relational databases, and they offer this, but there are also different kinds of database systems that offer different guarantees. And they're not better or worse, but it depends on your use case, which set of properties you want to pick. Also something, in case you want to revise your SQL skills, there's a very good website. It's a SQL murder mystery. And you're working for the police, you're in the crime scene investigation, you have various evidence in tables, and you need to connect the right dots in order to find a murderer. So this is something that I put in the past in the slide deck in greater detail for those who are learning SQL. If you want to revise your SQL, just do it. It doesn't take too long. I think if you have some practice, you can finish this in, I don't know, 15 or 20 minutes. If it takes you longer, probably there's a good reason to do that revision. So give a try at that, maybe during the Easter holiday. I found it quite interesting, just for fun. I found this 4 or 5 years ago when I created those slides, and also quickly solved the mystery, but it's a good practice. Now, we've seen these guarantees, especially ACID, and we will now talk about distributed systems. And in the context of distributed systems, we will also need to look at which guarantees distributed systems offer, big data systems that are distributed. And this links a little bit here to our introductory lecture, where I said a lot of use cases you're working on is you're just using your computer with a small data set and so forth. But now if you want to work on a big data problem and you just use your single laptop, computations may take very long. You train a huge neural network. Maybe all of that doesn't fit into your RAM or your disk. And if your computer crashes, you have a problem. So maybe you don't want to run a web service directly from your laptop, but you want to make sure you have some kind of redundancy, that the service is available and that the data is also backed up. This is the reality, and we can address this with distributed systems. And in a distributed system, we have multiple nodes, and these nodes need to communicate with each other. And I have a figure here that I found in a paper a few years ago, which I think overall is quite useful. So we have multiple computers in here, and maybe later we don't talk about computers anymore, but about nodes. And we could say we have, now let's use the term computer. We have a computer that runs some application. We have a local operating system, maybe Windows, and then we have another computer that runs a different application on Linux and on some Linux like Debian. And then we have two other computers that share an application. So the application B runs on these two computers. Maybe there's an Ubuntu and a Mac, and this application is shared. And somehow all of these computers need to communicate with each other through a network. And what we typically then have is a middleware, so a distributed system layer. And this allows us to provide some abstractions so these applications can talk to each other, but we don't need to worry too much about the local operating system because all of this is done by the middleware. And I'm just using a level of abstraction. And I maybe also don't care too much if the application is run on 1 or 2 computers. Maybe I just want to communicate between applications. And obviously I need a network, but the middleware takes care of all of this, that I don't need to worry about low-level implementation details of the operating system or the network, but I just have a higher abstraction. So this is what a middleware would do. And distributed systems have been common for a very, very long time. And in recent years, so for the last 10 to 15 years, cloud computing has become more popular. And I want to know from you what you're using cloud computing for example, as an end user or as a coder when you write larger applications. Maybe some of you have done this during your internship or some other job. So any contributions you want to make, you're most welcome now. How are you affected by cloud computing? How are you using cloud computing? And you can go ahead, and if there's anyone online, just raise your hand in the Zoom participant section, please.
Yeah, the company I work with, all processes done on some external servers. So cloud computing, so all the devices where, yeah, I would say like normal user devices, just to have a stable connection to the server, and then all the higher models and so on were trained on the specific servers.
Mm-hmm. Okay. We also got something here in the chat. One student used cloud infrastructure when training a model on a training set. Yes, especially if it's maybe a large data set, you cannot run this on your local computer. Now, any other suggestions about clouds, how you're using it or what it's useful for? Yes. Okay. Yeah.
Yeah, and also we had so in the time of application we created like a service for our company, and all the new customers they provided us all their data for their applications also via cloud computing, because on one hand you can't handle this amount of data with the physical representation only, and also in time of the globalization you just can upload it, and it's a lot easier also to share all the stuff with colleagues from different continents.
Mm-hmm.
So
yeah, thanks for all these contributions. So the cloud means like we look at AWS as an example. You can buy computing time there, but you're not buying time on a specific machine. Rather, at AWS, so Amazon Web Services, they have a lot of servers distributed all over the world. So it's a distributed system, but you're not accessing individual machines. Rather, you get a virtual machine that you can customize with the size that you want. And then it's mapped somehow to this IT infrastructure, but this is taken care of by Amazon Web Services. You're just paying for the time or the size, whatever, of your virtual machine. It has various benefits. You can easily scale up and down. Maybe you can fire up new virtual machines, or you can scale down again, so depending on the load you have. But you can also easily amend a virtual machine by maybe just adding more RAM to it or more storage. It's something that would be more difficult on a real computer, just to add more RAM or remove RAM. Maybe you have to shut it down for that, but a virtual machine, it's all virtual. It's mapped to a real environment. So this gives you plenty of advantages, in fact. And in terms of costs, you can just easily use this to scale up and down. There is not just obviously AWS, there are plenty of other providers, but it's very important. The cloud is not a silver bullet. It also comes with consequences. The question is the cloud always cheaper? that's disputed. The cloud is helpful if you easily want to scale up and down. If you just want to run a lot of computations for a very, very long time, maybe it's cheaper if you set up your own infrastructure for that. But then you could use the cloud on top for scaling if needed. But setting up your own infrastructure, you can run also in all sorts of, IT security issues, and you need to maintain the infrastructure. You need to worry about backups. All of this is taken care of in a cloud environment. So the cloud environment makes it much easier. Probably it's also much safer in terms of cybersecurity, unless you run into this nightmare that Microsoft has, or I don't think still has, that some keys to accessing the infrastructure were public. Maybe you heard about this, and there were some master keys, and I think they ended up in some Git repository somewhere. That's obviously a nightmare, and that has to be solved. But you don't need to worry too much about IT security. Still, you may have to update the software you're running in your virtual environment, but the outer infrastructure, there's a lot of support for you. And if you build your own infrastructure from scratch, you need to worry about updates and cybersecurity much more. What some companies do is they have their own servers, and then this is for the bases and the data storage, and then they use the cloud in order to scale up for computations and scale down. Some companies are only in the cloud. Nowadays, buying GPUs from NVIDIA seems to be challenging. So maybe one way to access them more easy is through the cloud than trying to buy them yourself on the market. But there are all sorts of things that can also go wrong with the cloud. When you work with a cloud provider and you put in very sensitive data, you need to worry about an NDA, so a non-disclosure agreement. Because you may want to talk to their support or their staff, and then what information can you share in those discussions or in the cloud? And if you want to do such NDAs with cloud providers, at least the ones from the US, it often tends to get very tricky. I've also had this when I worked in industry. We had a lawyer, they had a lawyer, and somehow we didn't make progress with fundamental things. And finally, we had an NDA with a cloud provider. I'm not saying which one, because they may be watching the video, because some of them are linked to me on LinkedIn. And I posted a link to the lecture recording on YouTube via LinkedIn. But what our lawyer noticed was we just didn't come to any terms with them because it was so difficult to agree on fundamental guarantees we wanted from them. And eventually we noticed the whole NDA with that cloud provider would only be with their staff in the German subsidiary. But their cloud infrastructure runs in the US or with a different subsidiary. And once they talk from this German sales subsidiary to their colleagues in the US or a different subsidiary, that would not be affected by the NDA. So doing NDAs with cloud providers can be very tricky. It's something you start worrying about once you're a manager and you're responsible for this. So pay attention. What I've also noticed in companies is some cloud providers, in this case AWS, they were so happy to help a subsidiary in a company where I worked, and they wanted to help them building their own AI use cases using AWS, and they would send like 2 or 3 data scientists for free for a month to that subsidiary. I was concerned about that from the beginning because I felt, well, they're going to make some revenue through the subsidiary, but probably it's not that enormous that it pays off, 1 month's salary of 2 or 3 engineers. And they came, I wasn't too happy with that, but they came, and eventually I think they were more interested in getting access to the data, learning about these processes in mechanical engineering. And they built a use case for free. They did that. But a few weeks later, they offered this as a base service through AWS to everyone, including the competitors. So there is no free lunch. If you get an offer like this, maybe turn it down, because they're not your friends that just want to help you use their infrastructure. They also want to understand your processes. I mean, AWS is something really good and something very helpful, but they obviously lack expertise in mechanical engineering, in chemistry, whatever. So they try to help you with your use cases, to also learn from you and then offer this kind of stuff on their own. So I'm not sure if this is what you want. And then if you use the cloud too much, you're fully dependent on AWS or Azure or whatever, and they can shut you down any moment. If you remember the US election in 2020, there was this pro-Trump social network that heavily supported him. And then after this riot around Congress, I don't know which cloud provider it was, they just shut down that social network immediately, and then it was off. So if your whole business depends on one cloud provider, you can easily be out of business, not just because of riots and political directions, but maybe they consider you just an opponent at some point. Maybe you use AWS to build your own bookstore or something, or your own video streaming portal, and at some point they consider you too important and they just shut you off, or they give you 1 month notice, whatever, and then you're out of business. So pay attention with that you don't get considered a challenger or whatever, and always have a backup strategy. And especially a lot of companies I deal with, they have their own infrastructure and they use the cloud for scaling or for extra training, whatever. But you're fully dependent on the cloud, you can run into so many problems. We have a few minutes left. We have finished with distributed systems. Next time, I'll talk about MapReduce, and we'll advance with this big architectures chapter. What I proposed in iLearn is next week, Tuesday, is not a public holiday, but somehow a lecture-free day, because they assume you're leaving before the holidays, you're coming back, and on Tuesday, you're sitting in a train. But I guess many of you are somehow available. So I would be offering the course next week, Tuesday, from 10 to 1 online. So I won't be here. And if you miss it, but I guess many of you will be joining, if you miss it, there's a recording. This will also help us to speed up a little bit with the content, so you can also start preparing your seminar presentations earlier if we advance a little bit quicker with the content of the course. So it's next week, Tuesday, from 10 to 1, and we'll be recording. Nonetheless, I would be happy to see many of you in the online sessions. So it will be purely online, and there will be a recording. And maybe in 2 weeks or so, I'll also start saying more about the seminar presentations, and then you have plenty of time to prepare them. If there are no more questions, we're done, and enjoy the Easter holiday. Take care.